What's up, everyone? It's a new week and welcome back to my video. So as promised, we're going to look at two more examples of inequalities of polynomials and try to see how we can use the tricks, or to be more accurate, the ideas that we have found in the last video to help us solving the inequalities of polynomials. Okay, so here are the two problems. First one, we have x to the fifth power plus 10x cubed plus 2x squared plus 5, which is greater than or equal to 7x to the fourth power plus 11x. Where the second problem says 5x to the fourth power is strictly less than 2x cubed plus 18x squared plus 14x plus 3. Okay, so before we move on to the solutions, you can pause the video and try yourself. And also don't forget to like and subscribe to my channel to find out more of my other videos, and turn on the notifications so that you won't miss any of my new videos either. Okay, are you ready for it? Let's go. So the first problem, we have something that is a little bit scary because we have a quintic expression, meaning that we have a degree 5 expression, and perhaps some of you already know that there is no general solution, like what's so-called formulas for degree 5 or higher polynomials, such as whatever called quintic equation or quintic formula or so on. So how can we actually find the roots? Well, first of all, in order to use the trick that we learned in the last video, we first need to make sure that one side is 0. Well, usually we'll of course put the right hand side to be 0, and then for the left hand side, we would like to break the expression into some terms. In other words, we want to factorize it as much as possible, so that each factor is actually reduced into lower degree, and hopefully we can even just factorize it into a linear term, so that we would just know the solutions or the roots right away, so that we can then figure out which regions we want. And again, since we're solving inequalities, not an equation, we're not trying to get the roots itself or the single points. Instead, we're actually taking those points and then try to take everything in between every two consecutive roots as a region, and decide which regions we would like to take as our answer. So since we don't have it yet, what should we do? Of course, first we gotta move everything on the right hand side of the inequality to the left hand side, so that now we get the following. We have x to the fifth power minus 7x to the fourth power plus 10x cubed plus 2x squared minus 11x plus 5, which is now greater than or equal to 0. Good. Next, we need to factorize it. Well, good thing is we can actually do that, but how do we do it? Well, we're going to use something called the factor theorem, which is actually perhaps you have learned it in algebra class, which says that excuse me, which says that if we know some roots a is some number a is a root of the polynomial expression that we have, then the term x minus a is one of the factors of the expression. So here we can actually try some numbers, some nice number, and see if we're lucky enough to actually get that this term is going to be 0, so that we can say that x minus that number is one of the factors of this expression. Let's try 1. So we see that we have 1 to the fifth power, which is 1, minus 7 plus 10 plus 2 minus 11 and plus 5. And if we add them all together, we should actually get the expression equal to 0. Meaning that 1 is one of the roots. So x minus 1 is actually one of the factors. So we can just keep reducing this expression by the factor theorem, so that we eventually will end up with the following. We actually get 3 copies of x minus 1, and then for the remaining parts, we will actually get x squared minus 4x minus 5. And then of course, which is still greater than or equal to 0. Good. And now, for the second part, we still can actually reduce a little bit more. In other words, we can try to factorize it, so that now we will actually get 2 more terms, 2 more linear terms. So this is obvious enough. We actually get x minus 5 and x plus 1. So we will have x minus 5 times x plus 1. Then next, we already have all the factors in linear form. So we actually know all the roots of the expression of this polynomial. But in order to use the trick, again, we need to first rearrange the order in an increasing order. Meaning that now we see that there are 5 roots in total. Well, even though one, there's a triple root, we still need to put them in order from which is -1, 1, and 5, like this, so that we can actually use a trick. Then, following from it, we can use the table and check it quickly. Let's call it f of x, or you can just put y. So we have the 3 distinct roots, where the root in the middle, x equals 1, is actually not a simple root, meaning that it has a higher power than 1. But anyway, we know that at these 3 points, the y value must be equal to 0, because we can just substitute in, seeing that when x equals -1, this term goes to 0. When x equals positive 1, the middle term goes to 0. When x equals 5, the right term goes to 0. So we get the product of 0. Good. Now, let's see, what do we do next? Again, we have the coefficients, the leading coefficients especially, is positive 1. And since it is already positive, it means that from the shape of the polynomial, which is a degree 5 polynomial, a quintic polynomial, a quintic expression, when x is getting larger and larger, meaning that when it's approaching the positive infinity, the y value is also be positive infinity. So we can just check it quickly, right? Let's say x equals 10. Then the first term becomes 11, which is positive. The second term is 9 cubed, which is positive to odd power, so it's still positive. And then the last term is 10 minus 5, which is 5, and it's still positive. So we end up with positive on the right-hand side of this chart, as always. Then now we just need to check. Since the root 5 is in degree 1, we know that there's a sign change when we pass through the point. Meaning that if we end up with positive, then before passing the point, the sign is negative, or the y value will be negative. Similarly, when we check this point right here, the root x equals 1, this root has a degree 3 here, meaning that it also has a sign change when the function passes through this point. So it means that it has to be positive before hitting the point, and then it turns down to negative. Now, last but not least, we need to check this one as well. So again, this is degree 1 is odd degree, so we also have a sign change here. We end up with negative here. So what do we want? Well, since we want the y value to be greater than or equal to 0. In other words, we want it to be 0 or positive. Let's see what we have. We have negative here, which is not what we want. And then we have 0, which is included. Very good. And then we have positive here, and then end up back with 0 again. So we're going to take everything here. Then we have a negative. So we will cut off right here. I'm not going to take the negative part anymore. Then it's going to turn back to 0 and then positive. And again, we need to include 0 in this case because it says equals greater than or equal to 0, which means we include 0. And then after that, everything is positive. So we're going to take everything in the blue boxes. Okay, so what do we end up with? Our solution will then be between -1 to +1, as we see. And of course, we have to include both endpoints, as the endpoints are going to give us y equals 0. And then we will just take the union, meaning that we will just combine with the other parts, which is x is greater than or equal to 5. And again, we have to include 5, the endpoint, because we also need to include y equals 0. So that's it. We now finish the first problem. Woo! Good. So let's move on to the second one. We're going to do the same thing. For the second one, let me factorize it. So again, since we don't have 0 on the right hand side, we need to move everything to the left. And we're going to get 5x to the 4th power minus 2x cubed minus 18x squared minus 14x minus 3. So we turn all the things on the right hand side to the left hand side and switch the sign, so they all becomes negative, which is less than 0. Good. Now we need to factorize it. Of course, if you already know the quartic formula, meaning that if you know the formula for solving any general degree 4 polynomial, you can use it. But since this term is luckily factorable, meaning that we can actually break it into 2 or more smaller, 2 or more factors with smaller degrees, we might as well just do it so that we can actually get something that is easier for us to calculate without actually knowing extra ideas like the cubic formula or even the quartic formula. Good. So what do we get? We actually will get something like this. Since we have a 5 here, we actually can, and we have an x to the 4th power, we can try to break it into 2 quadratic factors, meaning that they're both degree 2. So if we do that, of course, here we have to break the 5 into 5 times 1, and then we will get 5x squared times x squared, okay? And then after that, we just need to do long divisions, and also you can just try to check other stuffs to see what we will get. And the nice thing is we actually get a result like this. We have 5x squared plus 8x plus 3, and then we're going to get x squared minus 2x minus 1. Good, which is less than 0, of course. Now, the first part, we can actually factorize it one more time. Again, depends what way you want to do. You can use the cross multiplying to check yourself. So this term, it will turn it down into 5x plus 3 times x plus 1. Excellent. Now both of them are linear. But how about here? Can we factor this? Well, unfortunately, this really looks like x squared minus 2x plus 1, right? If it is plus 1, we know that it is a perfect square. But we have a minus 1 instead. So if we are going to factor it, what will it become? Actually, most people will argue that it is not factorable. but that's only if the coefficients are integers. So again, we cannot really factor it if we want to keep it in the very nice form that all the numbers are integers. But since this is just a quadratic expression, we can just use the quadratic formula to help us getting the answer quickly, or the roots, I should say. So if we do that, we will have 2 on the bottom because the coefficient, leading coefficient is 1. And then on top we have negative b, which is negative of negative 2, which is positive 2, plus or minus b squared. So we will have negative 2 squared, which is positive 4. And then minus 4ac. Well, a is 1, c is negative 1. So we have minus 4 times negative 1, which is plus 4, giving us 8 inside the radical. And we can just rationalize it to get something like this. And then after that, we can just simplify it. Divide both terms by 2. So we actually found the roots. 1 plus radical 2 and 1 minus radical 2, respectively. So what are we going to do? We're now going to brute force it a little bit. We still actually will break it into two factors, and we know the we know that the roots of this expression are not that pretty, but we still can write it into the following. We know that one of them is 1 plus radical 2. The other one is 1 minus radical 2. Good. So now we have 4 terms. I shouldn't say 4 terms. 4 factors in linear expressions. So of course, the first one we still need to adjust it because the leading coefficient is not 1, it's 5 instead. So what can we do? We're going to factor out the 5 so that we will get x plus 3/5 for the expression. And then, of course, we have everything the same, like this. And again, does the 5 matter? Not at all, because we can just divide both sides by 5. 5 is always a constant. It's never going to be equal to 0 in this case. So we can divide both sides by 5. And more importantly, 5 is a positive number. Since we divide by a positive number, we don't have to flip the sign at all. So we can now technically erase the 5 without affecting our result. Good. So last but not least, we now need to put the factors in an increasing order like what we did, so that we can later on use the idea. So how should we do that? First, we see that this number is definitely positive because we have positive 1 and then we have positive radical 2, and add them together, it has to be positive. So we can guarantee that this will probably be the last term that we are going to write down. And why? Because everything else, well, this is negative, this is also negative. And this is probably negative. We will check why, okay? So let's stick with this first. We know that this is this must be positive. Now the question is, how do you know that this is negative? Well, simply we argue that radical 2 must be bigger than 1. Because we can just square both sides and see that 2 is greater than 1. Okay, so if radical 2 is bigger than 1, then 1 minus radical 2, meaning that we have distance 1 here, and then we're going to subtract back by radical 2. So it has to pass the zero mark and go to the negative side. So we see that this is somehow negative. And how negative is it? Well, in other words, what is numerical approximation? Radical 2 is approximately 1.4142, and yeah, we don't need that many digits. So we know that if we have negative of this, we'll get approximately negative 1.4142. So if we have 1 minus radical 2, this is approximately negative. We're going to add 1 back so that we now get negative 0.4142. Now, why does it matter? Because now we need to compare this value with the other two values that we didn't put yet. So we know that here we have negative 1, which is strictly less than this, obviously. Now this one is negative 3/5, or in decimal, we know that is negative 0.6, which is actually smaller than it. Is actually on the left side of this value. So now we know that the order of these three will be x plus 1 or x minus negative 1, and then times x plus 3/5. Again, this is actually the smallest. This is a little bit bigger, and this is bigger than the other two. So we'll put this after, like this. So everything is ready. Now we can make our table. We have again x as our first row, and then y value, or f of x, which is the function of the polynomial we have in our second row. And then we're going to list all those roots on the first row, and here we need to put them in an increasing order, like this, so that we know what to do. And again, since those are the roots, their y values will be 0. Now, last but not least, again, we need to use the shape of the expression. Since we know that this is a degree 4 polynomial known as a quartic polynomial, the shape of quartic polynomial, especially as we know that the roots are in degree, well, each root is in degree 1, or I should say, each root is a single is a simple root. Then we can just simply use the first idea that we have. We know the shape is kind of like a W, and then it will pass through the x-axis 4 times. So we see that we will start with positive, then negative, positive, negative, positive, positive, negative, positive, negative, positive. So again, if they're all simple roots, then we always know how the shape will look like, and also know that which regions we definitely would take. Since we want the expression to be strictly less than 0, first of all, we cannot include any endpoints. Then, as we want the y value to be less than 0, we start with positive. We will take everything in between. So we actually will end up with negative 1 is less than x, which is less than negative 3/5, and then union with 1 minus radical 2, which is less than x, less than 1 plus radical 2, and that's it. We have our solutions now. Whew. It seems pretty long, right? But if we just try to write down the steps, we can actually get the answers quickly. So that's it for this video. I hope you all enjoyed it. I will see you guys next time.